Then our last speaker is Maria Tzortziou.
Okay, so I will be discussing about linking in situ and satellite measurements of CDOM optical properties to DOC dynamics and results. Oops.
Click right there.
Yeah.
There you go.
And results are based on measurements we had across a range of tidal marshes, freshwater, brackish, salt marshes, mainly along the eastern U.S. coastline. So continuous measurements are critical for understanding marsh airstream variability in marsh airstream biogeochemical exchanges. So we use an XO2 water quality sonde for measurements, continuous measurements of water physicochemical and optical properties, such as CDOM fluorescence. And here you see results for one of our intensive study sites, the Smithsonian Global Change Research Wetland along the western shoreline of the Chesapeake Bay. We found that we get better predictions for DOC in this system when we're linking DOC not just to CDOM fluorescence, but also parameters such as temperature, pH, and DO, dissolved oxygen, because these physicochemical properties provide information on environmental conditions and variability in the CDOM fluorescence to DOC relationship. So here you see estimated DOC versus measured DOC with an R-square of 0.73. Now, using these estimates of DOC based on continuous measurements of CDOM fluorescence and measurements of water flow, we estimated DOC fluxes. And here you see estimated monthly DOC export from the marsh to the estuary. And first of all, you see strong variability. These are different months. Overall net export from the marsh to the estuary, but strong variability. And using these measurements to estimate the net annual export of DOC from the marsh to the estuary, we actually found an export that was 2 to 3 times higher than previous estimates based on 1 or 2 individual tidal cycles. So 2 points I wanted to make here. First, that continuous measurements are critical for understanding variability in DOC fluxes and get accurate estimates of net annual export of these systems. And second, when we use optical sensors, we need as a community to discuss more about corrections we apply on these sensors and how we go from optical quantities, proxies, to DOC concentrations. Now, one technique to have frequent observations of carbon dynamics in coastal systems is satellite remote sensing. But applying satellite remote sensing to get DOC dynamics in wetland estuarine interfaces can be very challenging, first because of the bioptical complexity of estuarine systems, and second because of the coarse spatial and temporal resolution of most ocean color sensors. So we recently developed a new algorithm to retrieve DOC from space, and we're addressing some of these challenges in 3 ways. First, we use the full satellite measure spectral information to retrieve not just CDOM absorption magnitude, but also the CDOM absorption spectral slope from satellite observations. And then we retrieve DOC not based on the highly variable spatial, regionally, seasonally dependent relationship between DOC and CDOM absorption at one wavelength, but based on the strong correlation between the DOC-specific CDOM absorption and the absorption spectral slope, 2 parameters that depend only on the quality of DOM. So you can get a very tight relationship between these 2 quantities. And then we apply this algorithm to satellite data from a sensor that has a very good combination of both spatial resolution as well as spectral information. For example, MERIS has a better spatial resolution compared to MODIS, but more spectral bands than Landsat. And evaluating this algorithm to different, using observations from different coastal areas, the Gulf of Mexico, Chesapeake Bay, Delaware Bay, Long Island Sound, the Mid-Atlantic Bight. We had very good comparison with observations with a mean APD of 20% for DOC. applying this algorithm to the Chesapeake Bay, we looked at monthly composites of DOC from Mary's for 2009, and you see here variability in DOC from January to December. So first of all, in these kinds of monthly composites, you see the influence of different factors on spatial temporal dynamics in DOC, the influence of freshwater input from the Susquehanna River, the influence of wetlands, temporal variability associated to precipitation events. But what I thought was interesting was these very high DOC values in this area in the Chesapeake Bay, particularly for December. Now, people who are familiar with the Chesapeake Bay system, they would clearly see that this is an area where we have the largest marsh in the Chesapeake Bay, the Blackwater Refuge marshes. So it's reasonable to get high DOC values. But why in December? Well, these are monthly composites, so this is a combination of satellite scenes for different overpasses for Mary's. So we looked at the tidal stage of each individual Mary's overpass. And we found that for December, we had the largest number of low tide scenes compared to high tide scenes. And because of the influence of the marsh in this area, this is how a low tide Mary's scene for DOC would look like compared to a high tide scene for DOC. So 2 points I wanted to make here. First of all, that these algorithms, when you use satellite imagery that has the spectral information and the spatial resolution, they can capture the impact of wetlands on DOC dynamics in estuarine waters with higher DOC at low tide, but also higher sedum absorption and lower sedum absorption spectral slope. But then we need to be very careful and include information on tides, the tidal states, when we're interpreting this satellite imagery and when we're looking at these monthly composites, as well as when we're using these individual satellite images to compare with field observations.